Good afternoon, everyone, or morning if you are in the US, or evening if you're in Asia. A very warm welcome from our end in this CCU Symposium, Carbon Capture and Utilization. My name is Korneel Rabaey. I'll be hosting you through the afternoon and also be moderating the debate later on. So today's event has speakers from several organizations. I will introduce them separately when they are going to present. The symposium of this afternoon is a joint organization between Capture and EIT Raw Materials. Just a little word about Capture. This is a network we have in our area between different universities and institutes to drive excellent research and collaboration on the theme of resource recovery. We work on three different themes over here: on water fit for use, on plastics to resource, and on CO2 to product. And around these three themes, researchers from the different institutes and engineers come together, also with companies, to really set up joint projects and joint programs. And so in time, we hope to become a very efficient nationwide network for R&D in this space. As I mentioned, we are also supported by EIT Raw Materials. EIT is the European Institute for Technology. And via this institute, some of our major programs in the European Union are being funded. And this one, Raw Materials, wants to focus across Europe with teams and companies on the sustainable use of resources and the sustainable reuse. And part of that is also education. So we're very happy to, with the support of EIT Raw Materials, present you this symposium of the afternoon. Before we continue, I'll very briefly pass the floor to my colleague Elise Meerberg to present a local request.
Hello, good afternoon. Thank you, Korneel, for giving me the word. Indeed, today's seminar is embedded in the INSYS Hub project, which stands for Industrial Symbiosis Hub. This project is coordinated by Delft and has a number of international partners, which you saw listed in the slide before, among which Ghent University. The Industrial Symbiosis Hub is an EIT Raw Materials project, and it aims at bringing together cases from the industry with students from the university. So what we want actually is that students from different universities, from multidisciplinary backgrounds, work on actual cases from the industry. So our call today is that if people from the industry have interesting cases on industrial symbiosis that students in the group assignment can work on, you can always email me at the email address that is given in this slide. Thank you very much.
Thank you, Elise. So now let's go to the meat of the program. Just a quick note, as this is a fully online seminar, we will be recording the seminars, and you do not need to switch off your mobile phone, but rather we ask that you switch off your speaker and potentially also your video during the presentations. We will be collecting questions that you may have via the chat channel over time, and these questions, if we have sufficient time, we will cover at the end. There is a half-an-hour discussion session. So it's very exciting to see the program of the afternoon, because we're really going to look at CCU from different angles, going all the way from why are we doing it, and via a number of real case studies to upcoming technologies, and think also about the economics and the political aspects. And I'm particularly excited to see this whole attention for CCU. About 7 years ago, I went to a meeting of the EU in Brussels that was supposed to be on CCU and CCS. And actually, it was almost exclusively about CCS, because CCU was deemed non-realistic and was deemed not achievable within the coming decade or so. It's interesting to see how CCU has emerged, has really become a key focus point in Europe. And so what will be interesting this afternoon is understand a little bit more of the rationale behind this, why it's attractive, but also what the challenges are. So I don't want to take more of your time, and it's really a pleasure to introduce our first speaker of this afternoon, Professor Mark Saeys. Mark has worked for years in Singapore and returned about 7 or 8 years ago, if I recall correctly, to Belgium to take up a position at the Laboratory for Chemical Technology. And he'll be first discussing with us the rationale for capturing CO2 and doing something with it. If you want to read more about his bio and those of the other speakers, they were sent via email earlier on. I will not go on longer, just to save for the speaker their time. So Mark, it's really an honor to pass the floor on to you. Can you share your screen?
I know. Thank you for introducing me, Korneel. Korneel asked me to provide a rationale for CCU. I thought I'll turn it a little bit around and I'll present the case for rational CCU. And so let me start with the basics. We live in a carbon-based society. A lot of materials, energy carriers, contain carbon, and a lot of our current standard of living we owe to the availability of those materials and energy carriers. A carbon-free society is very hard to imagine. A lot of that carbon originates from fossil resources, but some of that carbon also comes from other sources such as biomass. All these activities lead to CO2 emissions and an increase in CO2 in the atmosphere. Now, for a long time, we've been told we would run out of carbon, peak oil have been around for a while. But if you look at this graph, you see that the reserves, known and proven reserves, are much larger than the carbon budget we have. The red block here is the total amount of CO2 we can emit this century and still stay below a 2°C limit. If we emit about 50 gigatons per year, the 2000 gigatons there are over in 40 years. And indeed, in the past 20 years, we've already consumed about half of the carbon budget. So running out of oil or carbon does not seem to be an issue. We have more of a pollution crisis than a resource crisis in the carbon space. Now, the planet Earth is, of course, a closed system. So carbon that was on Earth stays on Earth. And so that motivated us to look at a cyclic perspective. So we had a discussion, Korneel and me and others in the Royal Flemish Academy of Belgium, about CO2 and what can be done. And so I'm a chemical engineer and I like to think about reaction kinetics, reaction rates. And so the buildup of CO2 is a simple kinetic problem in a way. The CO2 is, of course, converted with the help of sunlight to biomass. This process is fairly slow. About 1% of the sunlight that hits the planet is converted in photosynthesis. And the efficiency of that conversion is 1 to 5%. These are fairly small numbers, but if they were higher, plants had to be black to absorb more of the spectrum. So fortunately, it's not that high. This biomass then, in a period of millions of years through geological processes, forms carbon reserves, fossil carbon, which then is in this century and the previous century pumped up to drive our carbon-based economy. And these fuels then are burned and lead to CO2, and that CO2 is again converted via photosynthesis. And so in principle, there's not a problem. The cycle is closed. As I said, the planet Earth is a closed system. The problem is kinetics. The rate at which we consume and convert the oil and gas to CO2, and the oil and gas is nothing but archaic or very old solar photons that are stored into CO2. That conversion back to CO2 is much, much faster than the other steps in the cycle. And if any one of you took an undergrad course kinetics, you know that if A to B is faster than B to A or B to C, then B builds up as an intermediate, and that's what's happening. CO2 is building up in the atmosphere. And so converting biomass directly to fuels and chemicals and materials helps to speed it up. But again, biomass grows rather slow. If you would convert CO2 emissions from a typical power plant, which is a soccer pitch in surface area, you need about 200 square kilometers of surface area, which is about the area of Brussels. And so this process is faster than the millions of years, but not fast enough to match our current lifestyle. And so we at the academy suggested that the chemical route should be developed to speed up this way using catalysis to convert CO2 with solar energy or solar derived energy back to fuels and chemicals. And this rapid route is what we call CCU. Of course, there's another way to avoid the buildup, and that's storage of the CO2, to put the CO2 back in the reservoirs where we removed oil and gas from. And so carbon capture and storage is indeed a technology to pump that CO2 back into the reservoirs where oil and gas have been taken from. I do not like the term storage because it seems a bit messy and long term. Now, this CO2 that's pumped in the reservoirs actually reacts slowly with the minerals that are available there and becomes a carbonate. And after 50 years, that CO2 is no longer CO2, but has in most cases become a carbonate and been stored forever, which is a very nice way of storing. And so if you think about storage or sequestration, it should actually be coupled by taking fossil carbon out of those reservoirs. And an idea I've been proposing for a few years now is that you imply a take-back policy. For every fossil carbon that's taken out of a reservoir, the oil and gas company should accept the CO2 molecule back in return. Of course, one-on-one is an ideal case. You can start with 10 versus 1 and then gradually change it to maybe even 2-to-1 ratios. So that's carbon capture and storage. It's really linked to oil and gas recovery. Now, what else has happened in the past years is a drastic decrease in the cost of renewable energy. Both wind and solar PV have reached levels that are below the cost of fossil energy, and that creates unique opportunities. As you see, the European Union is using more of that renewable energy in its mix. You see the numbers go up, and the target for 2050 has been recently revised to 55%. So this amount of renewable energy creates opportunities for carbon capture and utilization, because to me, CCU is, as in nature, a way of storing solar energy, but doing it faster. And so at UGent, we have several projects looking at CO2 conversion, CO2 upgrading to a wide range of products. But today I want to focus on two cases. The first is indeed storing that solar energy into CO2 in the form of methanol or diesel. Now, the concept is essentially nature derived. You take energy from the sun and you use catalysis to turn CO2 and water into solar fuels and chemicals. And so we had this idea of making a picture where you essentially put a faucet on the sun and tap that energy and store it in a pitcher, which is CO2. CO2 is essentially the container that holds that solar energy in a chemical form. So if your first target for solar fuel is hydrogen, then that hydrogen at a certain heat, and if you burn that hydrogen, you recover 100% of that heat. Now, if you store that hydrogen in the form of methanol or diesel by reacting it with CO2, you actually still store a significant fraction of that initial energy, 94% for methanol, the first solar fuel, and 90% for diesel, a more compact fuel that can be made in this way. And if you again go back to nature, you see nature does exactly the same. Glucose is just nature's form to store hydrogen into CO2. And so this all sounds crazy, but it's perfectly possible. There are proofs of concept, and here you see the German Minister of Science and Education filling up her Audi car, of course, with German-made solar fuel. And this car, I'm told, drove just fine. Of course, the question is cost, and cost of this whole project depends crucially on the cost of renewable energy. And so we've done case studies, and you often end up at double the cost of hydrogen produced from fossil fuels. But I like this study that I want to highlight. It's from my friend Miguel Modestino. He's a professor in New York University, and he's originally from South America, a very optimistic can-do person. And so he said, what would be the minimum cost? And he essentially calculated the material cost for your solar cell, connected an electrolyzer to make hydrogen. And if you do that, very optimistically, you come to prices that are really quite competitive. And so this idea, again, this paper is a few years old, but you can look at the hydrogen panels in Leuven that actually use this concept, connecting a cheap solar panel to a cheap electrolysis device, direct connection, no transformers or something. CO2 materials is another interesting route where you store the CO2 in chemical bonds for a longer term. And we're working with Covestro on this technology where they mix CO2 into polyurethanes for the production of mattresses and isolation boards. This is a way of adding cheap CO2 to high value products and selling it at high cost. So economically, this story is a lot easier to make. Of course, you need to have the reactors and the catalysts to make this work. And so within Carbon for Pure, there's a video on YouTube as well. We're actually making insulation boards starting from steel gas from ArcelorMittal. Now, an important part, I promised you to have a word or two about rational CCU. To do CCU, you always need energy. And so if we have, let's say, free electricity, renewable electricity, what do we want to do with it? What's the best use for that electricity to give us a reduction in CO2 emissions? And so, Bardau has done a really nice study on power to watt, where he makes that case that if we have a green electron, the biggest CO2 reduction for the buck is probably not CCU. The first thing you should do is replace power plants by solar panels and wind farms. The second thing is heat pumps. We're heating our houses with natural gas, or even worse. And if you replace that by green electricity, you get the largest CO2 reduction per megawatt hour. It's a very important metric when choosing where to use those electrons. And so we made a little case study for the steel industry, and that's an interesting one, as it's one of the largest emitters of CO2, certainly in Flanders. And they use carbon not just as an energy source, but also as a reductant to make iron. And if you believe high school chemistry, then this is a nice stoichiometric reaction which produces less than a ton CO2 per ton iron. This is ideal world. This reaction is not favored at room temperature, and thermodynamics always gets in the way. So if you look more realistically, you get emissions of a CO-CO2 mixture with a much larger footprint than what the calculations suggest. And so then you have to look at different options. What do we do with that steel mill gas? And later, Wim will discuss a case to make ethanol from that steel mill gas, but people are discussing CCU, making extra hydrogen and converting that CO and CO2 to products, or even replacing the whole steel plant using hydrogen as a reductant. And so we compared those cases, and let me skip to the bottom line. If you start with carbon-based steel making, you produce a little bit of electricity, but really not much. Most of that electricity is used within the plant. If you use CCU and CCS together, you need a little bit of electricity, but you can have a huge reduction in the CO2 emissions by making ethanol or methanol and storing the CO2 you can't use. You can, of course, say, well, we're going to convert all that CO2 to useful chemicals, but the amount of energy you need is tremendous, and if that electricity has a carbon footprint, then actually you could make things worse. Hydrogen-based steel making is somewhere in between. It gives a CO2 reduction, but it costs a lot of electricity. And so the impact of these technologies depend critically on the grid emission intensity. And so, yes, if we all use wind and solar energy, all these technologies are very promising. But you can wonder whether that's the best use of green electricity. And so that brings me to a few points I want to make. I think I convinced you that a carbon-free economy is unthinkable. Our standard of living is based on carbon-based materials. We need to focus on a carbon-neutral society where carbon-based materials come either from biomass or from CCU technology. Natural photosynthesis is too slow, but chemical engineers have a way of doing things faster. And solar-driven chemical technology, hence, is an important part of the puzzle. And I think we need a positive message in this context, and so we need to advocate the advantages of our carbon-based standard of living and find ways to introduce CO2 and renewable energy in the fuel and chemical cycle. So with that, I think I'm already a bit over time, and so that's what I wanted to share.
Wonderful. Thank you very much, Mark, for this very clear introduction to the topic. So if there were questions, you can put them in the chat channel, and we will leave them for after the session. And we're very happy now to announce our second speaker, and our second speaker is Dr. Simon de Corte. Simon is a graduate of Ghent University a number of years ago, and quite quickly after getting his PhD, he became an advisor at the technology transfer, and now he's evolved into being a strategic coordinator for our EU innovation programs here. And in that role, he's taking up coordination on our end for the North CCU Hub initiative, which is a very exciting initiative that he will present just now. So I gladly pass the floor to Simon to present the North CCU Hub initiative. Simon, the floor is yours.
Thank you very much for the introduction, Korneel. I will give you a flavor of the North Sea CU Hub initiative and its first implementation being the North Sea Methanol Program. This picture already gives a flavor of the context where the thing is going to happen. I'm first briefly going to introduce you about what we're going to do, where we're going to do it, and why we're going to do it. What are we going to do? Of course, we're going to do CCU. I think after Mark's talk, I don't need to go into details on what CCU actually is. So we use CO2. Important to notice here is that we use the CO2 from industrial point sources. So in this program or project, at the moment, we're not targeting the CO2 in the atmosphere. We're looking at CO2 from industrial sources. We want to combine it in a smart way with renewable energy, and we want to make products out of it and create an economy by doing so. Where are we going to do it? We're going to do it in North Sea ports. North Sea port is, of course, very close to the North Sea. And the unique aspect of this port is that it's located in 2 countries, in Belgium and the Netherlands. So it's really a transnational port area. And there's 3 sites in this port. There's the Ghent site, the Terneuzen site, and the Vlissingen site. We are now, in the next slides, I'm going to focus on the ambitions of the Ghent side of the port. But actually, there's a CCU vision and a CCU ambition of the entire North Sea port area. Why are we going to do it in North Sea ports? Here you see some reasons, and the main reason, of course, is that this region has a huge challenge. Because of all the industrial activity there's huge emissions of CO and CO2, and CO is most often being burned to CO2. It results in an annual emission of 22 million tons of CO2 in the North Sea port area, in this transnational port area. Of course, the fact that these emissions originate from industry, from point sources, represent a clear opportunity when having the ambition of doing CCU. So we want to make use of this opportunity and really turn it into an economic activity. We have other assets to do CCU. For example, there's a high grid connection present in the port area, giving access to renewable energy from offshore wind parks in the North Sea. There is a chemical industry cluster that uses C1 products, such as methanol and methane. There's space available, there's piping infrastructure available, there's storage infrastructure available, and we have strong innovation and knowledge centers with a strong track record in energy technology, in chemical technology, and in biochemical technology. All these assets really make North Sea port a unique area to do some piloting and some demonstration work for CCU. Now, what is the engine behind the North Sea CU Hub? So it's represented in this picture. It's also something that has been presented in Mark's talk. So we start with renewable energy, and this renewable energy converts water into a hydrogen gas and oxygen gas. The oxygen can be used locally. For example, the steel industry is using quite significant amount of oxygen, so there's a local use of byproducts. The hydrogen in its turn can then be combined with CO2. CO2 originating from the different point sources present in the area. And these two can be combined in a chemical synthesis plant to make chemical building blocks. There are several options for these building blocks. We're going to first focus on methanol, but that will come back later in the presentation. During the synthesis process, also heat is generated, and also this heat is used locally. So very important to mention is that we really have the aim to use both the CCU products, the chemical building blocks, as well as the side products like oxygen and heat. We really have the ambition to use them locally. And this really creates a new economy in the North Sea port area. So this depicts how the economy looks like. It consists of an exchange of different streams, different energy forms in the area. So there's CO2 and renewable energy coming in or being produced. This leads to different products such as methanol, but also ammonia and others, which are being produced through a variety of intermediates. And all streams are being exchanged locally. This really creates a circular economy and a circular industrial ecosystem in the region. And this is clearly the aim of the North CCU Hub. Few words on the North Sea Methanol program. Now, what is North Sea Methanol? North Sea Methanol is actually the first implementation of the vision of the North CCU Hub consortium. So North Sea Methanol is a demonstrator unit, but a quite significant demonstration unit consisting of two plants. First plant is an electrolysis plant, which has a 63 megawatt electrolyzer. To give an illustration, the current biggest operational electrolyzer worldwide has a power of about 10 megawatts. There are several plans to build bigger electrolyzers up to 100 megawatts, but clearly what we are presenting here is an order of magnitude bigger than what is operational worldwide. This electrolyzer can produce up to 8,600 tons of hydrogen gas annually, and this hydrogen gas can then be combined with 63,000 tons of CO2, resulting in a methanol production capacity of 46,000 tons per year. To give an illustration, in the North Seaport area, there's an annual use of methanol of about 350,000 tons. So this gives an idea of what we're planning to achieve in the coming years in the North Seaport area with the North Sea Methanol project. Who is up for the challenge? So there's a consortium of 20 partners, and it's really a multi-stakeholder story. You see them presented here on the slide. On the left side, you see the industry partners that are directly involved in the value chain. They either produce renewable energy, they deliver CO2, or they are off-takers of the chemical products that are produced in the processes. In the middle, you see industrial partners having a supporting role because they have piping infrastructure or storage infrastructure, or are developing innovative methanol applications. On the right side, you see the knowledge and innovation partners. You see the university, the local university with a strong track record in chemical and biochemical technology. You see the Capture Initiative, the host of this session. You see the Biobase Europe pilot plant, a unique facility familiar with the upscaling of bioprocesses. And you see two Flemish innovation clusters, one for energy and one for chemistry. All this is supported by the local governments and regional governments. So there's the city of Ghent, the province of East Flanders, and the North Seaport, transnational North Seaport company, who are really the oil in the engine and really driving this whole initiative. I'm going to give a few words on the roadmap and the innovation trajectory that is associated with the initiative. So here you see the different opportunities for innovation depicted on a scheme. In white, you see actually the North Sea Methanol program. So we're going to use industrial off-gases containing CO2, combine it with hydrogen produced by electrolysis and renewable energy. We have CO2 and hydrogen, combine it to methanol, and we're going to use it locally in the chemical industry. Now in blue, you see different opportunities for innovation. We can use other input streams. We can optimize the different processes. We could think of a platform molecule like CO, which is thermodynamically much more interesting to start from than CO2, and would drastically reduce the need of energy to do the CCU. We could think of other building blocks that we want to produce, such as ethanol or formic acid or acetic acid. And we could convert these building blocks into really added value products, such as proteins, esters, and fatty acids, which could really give economic added value to the region. So there's several opportunities for innovation, both in the pre-conversion processes, in the conversion of CO2, and also in the application of the produced products. This gives a view on the roadmap and the timeline of the project. We started in 2018 with a preliminary study which showed the potential of CCU in the region. Currently, the partners of the North Sea Methanol project are negotiating a joint development agreement in order to start this development. And the first implementation will thus be the North Sea Methanol demo plant, consisting of a 63 megawatt electrolyzer making methanol, making hydrogen that can be used to make methanol. In green, you see then the upscaling of the North Sea Methanol project. So we gradually increase the power of the electrolyzer from 63 to 300 up to 600 megawatts electrolyzer by 2030. And we also increase, on the one hand, the production capacity of methanol and the variety of products that we're going to produce. So next to methanol, we also think of producing ammonia and formic acids, two other products which are heavily being used in the region. In blue, you see the innovation trajectory. And it is the purpose that the innovation trajectory continuously feeds into the project with new ideas, new technologies, new processes, and new products to be developed, which should lead that by 2040, the North CCU Hub partners are ready to produce fatty acids, esters, proteins, and other high-value molecules next to the methanol, ammonia, and formic acid. Now, what is all this going to cost? Here you see a graph showing the costs and the revenues, the operational costs and revenues of the North Sea Methanol program. Now, looking at the costs, you see that a big chunk of this cost is determined by the price of renewable electricity. So cheap renewable electricity is really key to make this process economically viable. Looking at the revenue side, we can sell some of the byproducts, such as the heat and the oxygen. We can get some value from the ETS CO2. We can, of course, sell the methanol, which is the whole idea behind it. But you see that with the current prices of methanol, there's still a gap of between 25 and 40%, depending on the methanol price, to make this idea economically feasible. In order to fill up this gap, we're looking at different forms of subsidies to bridge the gap and to become economically feasible in the longer run. The good news is that the real momentum is there to make the thing happen. Subsidies are there to fill gaps, to support investments, and to make projects kick off in order to make them economically viable in the longer run. On a national level in Belgium, we think of a national energy and climate plan. We have a new industry innovation program called the Moonshot program, which will invest more than 400 million euros in the next 20 years on innovation to make the region more climate neutral. And of course, there's European opportunities, inspired, of course, by the Green Deal presented recently by the Van der Leyen Commission. One of the opportunities is the ETS Innovation Fund, which will be very important for this project, and where we're currently preparing our first proposal to be submitted in October. So I hope that this gave a bit of flavor of what we plan to do in the North Seaport area, that this area really has unique assets to do CCU, that the North CCU Hub Consortium is a multi-stakeholder consortium, and that we're ready to kick off our ambitions with the first implementation being the North Sea Methanol project. I'd be happy to answer your questions later on in the session. You can also ask them by email. You can visit our website, which is really brand new, and I would encourage you to follow us on LinkedIn. And to end, I would like to show a movie who is summarizing all this in a very nice and graphical way, making things even more clear.
Our planet is heating, The global temperature is rising fast since 1960. For a long time, scientists said that hitting this line will cause a spike in wildfires, mass migration, and it's going to cost us
more than $43 trillion.
That's what's going to happen if we stop here. Right now, we're on track to go way past that.
If action is not taken, it will take the planet into an unprecedented climate future if we compare it to what has happened during all of human evolutionary history.
The best way to lower the global temperature is to lower our CO2 emissions, and carbon capture and utilization can help us in doing so. CCU is the process of capturing CO2 and converting it to useful products. This circular reuse of CO2 can play a key role in the transition to a low-carbon industry. The way this works is, renewable energy turns water into oxygen and hydrogen. CO2 emissions and the hydrogen are used to make green methanol. This methanol and its side products, such as heat, oxygen, and water, are also used locally. An ideal location was quickly found within the North Sea port area. There are many reasons why the peninsula Rodenhuizen has been chosen.
In the North Sea port, there are large volumes of CO and CO2, up to 20 million tons per year, in relatively high concentrations and of high quality.
We have potentially large industrial buyers of chemical products and e-fuels, such as methanol and ammonia, with the ability to utilize the byproducts as residual heat, water and oxygen.
We have a high voltage grid connection with renewable energy from wind offshore in the North Sea. We can use that energy to produce hydrogen through electrolysis.
We have intense logistic activities with transport by road, rail, water and pipeline. We also have a lot of storage capacity and much space to invest.
We have a powerful innovation and knowledge cluster, strong in energy, in chemical and biochemical technology.
But who is up for such a challenge? 20 industrial and public partners will collaborate intensively. Large industrial partners can provide renewable energy or CO2 as a feedstock. Others are potential off-takers for the green methanol and byproducts. Some partners are specialized in piping infrastructure or storage facilities or create innovative methanol applications. The innovation part of the project is managed by specialized knowledge partners, the university, and 2 spearhead clusters, one for energy and one for chemistry. And all this is actively supported by public entities, the city, the province, and the transnational port community. This project started with a preliminary study in 2018. The first large-scale demonstrator will be up and running by 2024, called North Sea Methanol, producing green methanol, and will have an electrical capacity of 63 megawatt. By 2028, green methanol and ammonia will be produced, and the electrical capacity will increase to 300 megawatt. By 2030, formic acid will also be produced. Furthermore, the electrical capacity will increase to 600 megawatt. By 2040, the North CCU Hub wants to produce higher value chemicals, such as fatty acids, proteins, and esters. Along this roadmap, the innovation trajectory is continuously feeding the different large-scale demonstrators with new elements and applications. When all stages are up and running, more than 1 million tons of CO2 will be saved, captured, and avoided together. Belgium's national and regional governments plan the way forward with a holistic decarbonization approach. The region of Flanders commits itself to support CCU installations and the deployment of Flemish research and innovation channels, such as the Moonshot program. With the Green Deal, the European Commission has launched an ambitious plan to make Europe climate neutral by 2050. The overall ambition of the North CCU Hub is to prove that a real circular industry exists by creating new value chains as self-supporting businesses. A financial help will be crucial in the early stages of the North CCU Hub roadmap so that things can be demonstrated and the economy of scale will solve the rest.
So thank you very much, Simon, for this presentation. So as you can all see, this is a very ambitious, forward-moving project that we're very excited about. Now onto a project that is further still in its development stage. And so I'm delighted to now, as a third speaker of the day, before the break, introduce Wim Van der Stricht. Wim is the CTO Technology Strategy and CO2 and circular economy of ArcelorMittal, one of the largest steel companies in the world. So after studying at Ghent and doing a PhD, working for Alcatel Bell, he's joined in 2013 the ArcelorMittal Europe Innovation Team. And so he's in charge of developing ArcelorMittal's corporate climate plan. And at this moment, he coordinates very large projects, such as Steelenol that he's going to be presented besides Torero and Carbon to Value. With that, it's my pleasure to pass on the presentation to Wim.
Good morning. My name is Wim Van der Stricht, and I'm working for the Technology Strategy Department of ArcelorMittal. I would like to start this presentation by thanking the organizers for giving me the opportunity to tell you more about this innovative project at ArcelorMittal, where we will produce ethanol from carbon monoxide. Steel is responsible for 7% of global CO2 emissions. On the other hand, we also call steel the fabric of life, since we cannot imagine a world without steel. A very nice example of that is this building in the center of the city of Ghent, which could not have been realized without the use of steel. So we're facing an issue. We're producing a lot of carbon emissions with the production, but we cannot imagine a world without steel. Steel can be produced in various ways. We start from our raw material, iron ore, and in the first step, we need to transform this iron ore into pure iron. We can use a high temperature gas, carbon monoxide, or hydrogen as a reducing agent to remove the oxygen atoms from the iron ore, or we can also use electricity directly in an electrolysis reaction to produce pure iron ore. Nowadays, carbon is still the most used reductant in a blast furnace process to produce steel at high quality and on a large scale. In the blast furnace, we have a basic reaction where we have iron oxide reacting with the carbon, producing carbon monoxide and carbon dioxide. So the emissions of carbon dioxide and carbon monoxide are inevitable in this chemical reaction during steel production. Over the past decades, steel producers have been able to reduce the use of carbon at the production gradually to reduce CO2 emissions year by year. But now we are in a situation where we need to do a major transition and take larger steps towards carbon neutrality by 2050. As mentioned earlier, the primary steel production relies on fossil fuel-based energy sources that emit CO2. And we recognize the vital need to transition to clean energy to be carbon neutral. And this clean energy will be in the form of clean electricity, circular carbon, and carbon capture storage, also called CCS. Alone, each of these three clean energies can in theory be carbon neutral. But the reality is that the scale of investment in the infrastructure that will deliver clean electricity, circular carbon, and CCS is different, and the availability and access to them varies. As a result, we will use different combinations of these three clean energies to reach carbon neutrality. This means we can move faster to reduce our CO2 emissions. And where we deploy circular carbon technology, not only will we produce carbon neutral steel, we could also put steelmaking at the heart of circular economy by avoiding CO2 emissions from other industries. We will create recycled carbon materials to replace plastics, for example, or fuels. And one of our flagship projects in our roadmap to carbon neutrality is the Carbonless Technology Project at ArcelorMittal Ghent, also known as TINONO. The carbonless concept is basically recycling carbon into sustainable advanced bioethanol. We will capture the gases from our blast furnace. These gases will undergo a gas treatment, being a basic gas cleaning process and putting the gas at higher pressure and filtering out most of the CO2 to end up with a carbon monoxide rich gas stream. This will be injected into a number of bioreactors where we will have advanced microbes developed by Lanzatech to convert carbon monoxide into ethanol. This will result in a solution of a few percent ethanol, biomass and water. This effluent will undergo a distillation step to produce ethanol of high grade, high quality with purity more than 99%, which we can directly market into the fuel market or as a basic material to produce other chemicals. The water with the biomass is undergoing some water treatment steps where we will filter out the biomass, and this biomass will be gasified to produce energy and steam, and the remaining water we will do recovery of some materials like ammonia, and then it will be recycled into the process to reduce the use of fresh water in the whole process. To produce a biofuel with our process, we need to start from a biogenic source material. We have opted to use waste wood, which otherwise would have been incinerated, as a source material to produce, in a first instance, biocoal, and this biocoal will replace fossil coal in our blast furnace. This carbon will then effectively be transformed in the blast furnace into carbon monoxide, and via the conversion by the Lanzatech process be transformed into our bioethanol. Here you can see a picture of the ArcelorMittal plant in Ghent, where you will see the location of the blast furnace, where there is already an existing pipeline that will transport the gas towards the existing power plant Knippegroen, and there we will tap off part of the gas to send to the ethanol plant, which is located opposite of the Knippegroen plant. Investment cost of the ethanol plant is around 165 million euro. We will take off 90,000 non-cubic meters of waste gas per hour from our blast furnace and partially from our basic oxygen furnace, with which we will produce approximately 64,000 tons of ethanol per year. The greenhouse gas emission reduction that we will realize is equivalent to 80 million liters of gasoline. Estimated start of production is 2022. In the first instance, we will market the ethanol as a biofuel, as there is currently a demand of 7 billion liters in Europe alone. 2 billion liters for the industry and 5 billion liters for blending the ethanol into gasoline. For the future, we see also a market in other sections, being, in first instance, jet fuel and fuel for heavy-duty transport. In the later stage, the ethanol can be the base material for production of plastics such as ethylene and propylene. Total market potential we see by 2030 is 435 billion liters. If the technology Catalyst will be rolled out in the whole European steel sector, there is a potential production of 10 billion liters. And if you would add hydrogen to the gas mix, we would even be able to produce 30 billion liters per year. The environmental impact of the Carbalist technology is multiple. First of all, by the selection of our source material being waste wood, we avoid that this would be incinerated and produce CO2 emissions for the generation of power. Since we use the waste wood as a biocoal in our blast furnace process, we avoid there the use of fossil coal as a reductant. So we will have no emissions coming from the fossil coal in our steelmaking process. The ethanol can be used as a source material for the chemical sector or the refineries. So there we will replace the fossil sources of oil and gas. So we will have no fossil emissions originating from that. And finally, the ethanol will be used as a fuel and can then in the end generate CO2 emissions in the transport sector. To give you an impression on how the ethanol production plant will look like, there is here a small animation video. As mentioned, the gas will be captured from our blast furnace and will be sent via dedicated pipeline towards the Steenanol plant. It is the same pipe that sends gas to the Lippogroen power plant, so we will tap off part of the gas and send it across the road to the Steenanol plant. Here you have a nice view. We will go to the bird's view to explain more detail which are the different components. So on the left hand side you see here the gas pipe going via PSA units to pressurize the gas to the bioreactors. Next to that you have the distillation unit to produce the pure ethanol, which will be temporarily stored in 2-day tanks. The water will then undergo some water treatment process where we separate out the biomass. That biomass will be digested into biogas, which we will then use to produce power that will be used internally in the Carbalist plant. Here you have a recent view on where we are in the construction of the Steenanol plant. You can see here clearly the digester. You see here already the steel construction for the bioreactors. You have here the PSA, compressor unit will be there, electrical substation, offices, and the water treatment unit. You already can see also some steel construction to bring the gas pipe across the road. Here are a few new impressions of the production site. Thank you for your attention.
So thank you very much, Wim. I hope that everyone can hear me. So it's really exciting to see how we have projects in the pipeline and projects that are really already in a very mature phase under construction, starting to apply CCU in practice soon. So we're going to have a break now, as foreseen. So we will bring ourselves up to the exact right timing, a little bit ahead of schedule. So the session will resume at 3:30 Central European Time sharp. That's 3:30, and just for those internationally, we are now 3:07. So in 23 minutes, we resume with the fourth presentation. Thank you, and hope to see you again after the break. Good afternoon, everyone. I hope you enjoyed your small coffee break on a Friday afternoon. So I'm excited to host the second part of our CCU symposium, in which we have 3 more presentations followed by a debate. And so it's my pleasure to introduce our first speaker after the break, Dr. Deepak Pant. Deepak is a senior scientist at VITO, which is the Flemish Institute for Technological Development, and he's a specialist in electrosynthesis, particularly design and optimization of electrochemical cells. I know Deepak also is a very active communicator on science, very active on social media, and so I'm sure he'll give a great presentation. With that, it's my pleasure to hand over to Deepak, and please, Deepak, can you share your screen and unmute?
Yes, please. Okay. Yeah. Thank you. Good afternoon and welcome back after the break. My name is Deepak Pant, like Korneel said, and I'm working at VITO here in Belgium, and I'm also a member of Capture, together with Korneel and several other colleagues who are present here. And I thank the organizers for the opportunity to say something about the technological perspectives on CCU. So VITO, like mentioned, is the research and technological organization whose research mandate actually lies between a university and the industry. And CCU is actually an ongoing topic in VITO for some years now and is spread across different research units. So how VITO is organized, it's divided over 5 research units of sustainable energy, sustainable chemistry, sustainable materials, health and land use. And the topic of CCU is covered by the 3 topics of units of energy, chemistry and materials. And you will see obviously why that is the case. So in terms of CCU at VITO, I try to capture everything here in one slide. And I belong to the unit of sustainable chemistry. And one of the main research topics we are busy with is currently electrochemical CO2 conversion, where the main focus is on electrocatalyst development, which actually we are carrying out with one of another Capture partners, Professor Tom Brueggelmans from University of Antwerp. We have been very active on developing gas diffusion electrodes, which are an integral part of CO2 electrode reduction, but also bioelectro convergence. And I will say something more about it in the later slides. We are also developing reactors and stacks and upscaling them. And our colleagues are busy with also downstream processing. Apart from that, we have a unit on biotechnology, where my colleagues have been busy for several years now on converting CO2 into bioplastics, which means polyhydroxyalkanoates and polyhydroxybutyrate. And they have very nice facilities for doing this kind of conversions. Another set of colleagues are also working on algae, but instead of bioprospecting, we are busy with harvesting and biorefinery. And colleagues from sustainable materials they have already developed a technology called carbonation of steel slags, and it's actually being sold now currently as carbstone. So it's written TRL7, but actually it's TRL9. And in all of these projects that we are working on, it's always coupled with techno-economic analysis as well as life cycle assessment. My colleague Meet Vandal is also among the workshop participants, as I just saw her here. In terms of ambition, so what VITO has set itself is an ambition to establish a CCU pilot based on one of these approaches to produce. Some numbers are mentioned here. We will see if when we get there. But the target is to have in 2 years from now, to have a demonstrator actually on ground. And finally, VITO is a founding member of CO2 Value Europe, which is a kind of organization which is working very hard to popularize the topic of CCU over Europe, and it's based in Brussels. So it has a lot of industrial and academic partners, so it might be interesting to have a look at them as well. Now, before you can convert CO2, you need to capture it, and it's not always necessary to have a point source like a steel mill near you that you can do the conversion. You can also capture it directly from air at a low concentration of 400 ppm. But this is quite an energy intensive process. There are already a couple of companies who are working on direct air capture, but the cost of economics is not beneficial yet. Now, another point you have heard a lot about the link of renewable electricity with CO2 conversion, but the point is that technologies like wind and solar are dependent on weather and not always available all the time. So there is therefore a need for energy source that is available day and night. So VITO has been working on this technology of geothermal energy, which is sustainable and that supplies both electricity and heat at the same time. VITO is working now almost a decade now And we have a field site in Walmart in Kampen region, where also VITO itself is located, the headquarters. So what happens here is, in terms of direct air capture, you need a ventilator that supplies major flow of air, a filter with a solid to absorb the CO2, and eventually some heat in order to extract the CO2 from the substrate once it has been captured. At the end of this process, what you are left with is really pure CO2 that is ideal for use as a raw material and which do not need any further pre-treatment. And it is possible to capture such kind of CO2 using the heat and electricity which is generated from these geothermal wells. And these are the ventilators, pilot scale, already on site available at our facility. And the intention in future is to couple this kind of air capture facility with one of the conversion technologies to have an integrated capture and conversion unit at place. So that's the kind of ambition. Of course, I had not seen the presentation of Mark beforehand, to be honest. So I also started with the same premise about the renewable electricity and how its price have gone really down in recent years. So this is a paper coming from NREL, and what you see here is the drastic drop in the electricity prices starting from 2010, and this is more so in the energy or solar-rich regions like India, where the electricity prices are rather low at the moment. So the link between the renewable electricity and the CCU is very obvious, and I don't need to discuss that further. But I want to propose this, which I read in the Bloomberg News by Akshat Rathi, who is a scientist turned journalist. He decided to give these decades as 2000 as the decade of wind, the previous one of solar, the ongoing one as batteries, the next one as of hydrogen electrolyzer, and so on and so forth, as you can read there. This is, you can argue about it, or maybe this can be a point of debate as well, but I think it kind of makes sense if we look at the renewable energy perspective globally, which is going on currently. And even though it's in minority, the renewable energy source now comprise almost 25% of the global electricity capacity. So that provides a huge opportunity for CO2 reduction. Now, in terms of CO2 reduction pathways, you have can utilize electricity, you can have a direct or indirect routes. So you have reductive pathways, which include electrochemical, bioelectrochemical, plasma, thermochemical. And in fact, all of these are well covered by capture members. So the plasma work is going on in University of Antwerp with Professor Annemie Bogart. Thermochemical is going on at Ghent, bioelectrochemical, both VITO and Ghent. And the other part is non-reductive part, which you know very well, which are closer to market, like fertilizers used in Coca-Cola kind of food and beverage, enhanced oil recovery. So even though these non-reductive technologies are closer to market, but the opportunity for electricity utilization in them is rather low. So that's why this part is more interesting, because you can have both the aspects of RES as well as CCU there. I wanted to give some examples, and first one I included is indeed the dream production for production of polyols, but Mark already explained that very well. So this was also a project that started almost a decade ago, and now it's nearing its commercial realization. And in 2014, André Bardo and his colleagues did a life cycle assessment of this whole process. And what you see here is indeed that it does the new process leads in GHG reduction as well as fossil fuel reduction compared to the conventional processes. The current status apparently is that Covestro has decided to pursue its commercial utilization, and a production line has been established for 5,000 tons annual capacity with an investment of euro 15 million. Second example I wanted to share is about Carbon to Chem, which is also a large-scale project in Germany. Near the location of ThyssenKrupp in Duisburg. It started in 2018, and the idea is to convert CO2 to methanol and isocyanates there. LanzaTech is a very well-known name in terms of gas fermentation processes. They started in New Zealand, and they are now in United States for many years already. And they have quite a global footprint with a lot of pilot plants in China, India, and closer home in Belgium with the ArcelorMittal, as you heard just now. In terms of products that they are making, so they divided their product spectrum over 3 layers: discovery, lab, and pilot. Ethanol and 2,3-butane diols are close to pilot and demonstration. But then at lab scale, they are also working on isopropanol, acetone, and butanol. The whole conversion scheme is based on genetically modified Clostridium bug. And a lot of other products are at discovery stage, which will be carried out. Hopefully, it will be to the next stages as well. This graph shows some of their processes from Michael Kopp and Son Simpson from LanzaTech. So what you see here is the feedstock that their bugs can tolerate or use, which includes not only CO2 and syngas, but also industrial waste gases, which can be either directly or after a cleanup provided to the fermenter. And as a result, they can produce either ethanol, diesel, commodity fine chemicals. 2 months ago, I read the news that they have established this company called LanzaZ, which is now specifically dedicated to the jet fuel production starting from CO2. This is their pilot plant in China, which has been in operation for quite some time, which can take a feed of syngas in this ratio. And at the end, the output is mainly a product, which is ethanol with only traces of acetate, butylenediol, and biomass. In terms of electrolyzers, so that's the other technology that's gaining ground not everywhere in Europe as well as globally. And you can classify the whole systems based on the operating temperatures. So if the system is running at less than 100 degrees, then you have 2 types, planar aqueous H cells, which is the conventional configuration, which have an anode and a cathode, oxygen evolution happening at the anode, and hydrogen and CO2 reduction happening at the cathode, separated by a membrane. You can also make a MEA, membrane electrode assembly type of stack, and it is easier to stack this, which also include a gas diffusion electrode. At the higher temperatures, you have the proton ceramic electrolysis cells as well as solid oxide electrolysis cells. And so far, I read somewhere that almost more than 20 reduced products have been reported, which includes also aldehydes, ketones, carboxylic acid, glycol, alkane, and alkene. So the CO2 electrode reduction is actually quite an interesting topic at this moment. The next part is combining the two, which is combining the electrochemical part and the biological conversion part. And you get a concept of electrobiorefinery. So refinery, as you all know, is something where you process the biomass to produce fuel, power, and chemicals. In terms of electrobiorefinery, you insert an electrochemical step at different conversion stages. So you can have also in pretreatment as well as bioconversion. Then you have a concept of either electrofermentation or a microbial electrosynthesis system. And you can also use electroseparation for downstream processing. In fact, the lab of our moderator, Professor Rabaey, has made some rapid strides in this area in recent years. Now, I promise I will tell you something about the GDEs that VITO is working on, because they are an integral part of not only the electroconversion setups, but also bioconversion setups, in the sense that you can use enzymes which can be then immobilized on the electrode surface, as shown here, or living cells like bacteria, or electrocatalyst. And we are working on all 3 aspects here. The advantage here of shifting from a submerged reactor to a gas diffusion setup is that to overcome the mass transfer limitations of CO2 supply to the electrolyte. And these steps, kind of electrodes, have also been used by our industrial partners, such as Indian Oil R&D Center in India. And currently they are building a microbial electrosynthesis pilot of 500 liters to upscale this further. Now, in terms of electrode itself, consists of 3 layers, a gas diffusion layer, which only allow gas to go in one direction. So it's completely hydrophobic. Then you have the catalyst layer, and you have a current collector. We started with carbon-based electrodes. Eventually, for electrode reduction, we are now working on copper and tin-based electrodes. And with one of the set of electrodes that we developed last year, we can actually reach current densities of 250 milliamps per centimeter square, which are close to the commercially relevant current densities, as they say. Then you can have another set of combination of conversions, where in the first step you carry out electroconversion and then followed by the bioconversion. So here what you have seen is a CO2 electrolyzer, which is converting CO2 into syngas with a catalyst like gold, whereas with another set of catalysts you can directly have hydrocarbons. So, and then this kind of syngas and hydrocarbons then can be taken to a second reactor, where the engineered enzymes or the bacteria convert it into long-chain commodity chemicals. Now, one of the real-life examples of this is a company in Germany called BFAB, and they are developing something they call as formate bioeconomy. Don't go by this, these are German words. We wrote recently a chapter with them, which was published in a German version of a book. So that's why the abbreviations, but the concept is clear, I think. In the first step, using renewable electricity, they are converting CO2 into formic acid, and that formic acid or formate is then upgraded using a microbial conversion system. So this is actually a C1 bioeconomy, they say, to produce products like animal feed or chemicals or directly as fuel. So that's about BFAB. Then you have also one of the most advanced and the oldest technology of thermochemical conversions, where you use heat, pressure, and inorganic catalysts to make directly hydrocarbons and oxygenated products. In terms of technological readiness level, this is actually the most advanced form of CCU. And the best example for this is indeed the carbon recycling plant in Iceland, which is known as George Ola plant, already operational for more than a decade. And in terms of technology, I think this is world's largest CO2 to methanol facility, producing almost 5.5 kilotons per year. It also uses locally produced CO2 and hydrogen. And of course, if you will recognize this word, geothermal energy, because that's what they have there. So they have a kind of a cheap source of electricity to carry out. And this methanol is then supplied to different markets, including mainland Europe, and it comes to Amsterdam and Rotterdam. From there, it's taken up for further conversion by industries. They also established a second plant. This was from presentation they gave in 2015 in Germany, which is now producing 400 tons per year of methanol. Another company from our neighbors, Netherlands, is Photanol, which is basically working on algae, cyanobacteria, and they use genetically modified versions of it. This is a spin-off from Vrije University of Amsterdam to make biochemicals such as lactic acid, and they want to target cosmetic industry as their clients. In 2018, they actually received closed funding of 8 million euro to build a demonstration plant at ExxonMobil in Delfzijl, which is also in Netherlands. Now, from the perspective of circular carbon economy, one of the popular topics is indeed the power to gas or methanation. So conversion of CO2 into methane, and then methanol can be supplied by the gas grid and used as a fuel. This is also a concept which is quite popular, gaining a lot of ground and close to commercial realization. Two representative examples here are companies called Corte, and other one is Electroarchia, which is based in Germany. In fact, Electroarchia already in 2014 developed a 6.7 million euro project in Copenhagen to construct world's largest commercial power to gas system, which consists of a 1 megawatt alkaline electrolyzer plant. And recently I read in the news that they also received a funding of more than 10 million to build this concept further. Now, in terms of comparison of products and the technologies and how far they are on technological readiness level, you can have classified them in terms of ease of formation. Now, this is a concept which was given again by NREL researchers. They classified it into 4 criteria like rate of formation, partial current density, Faraday efficiency selectivity, energy efficiency, and current TRL. And based on these, you can see carbon monoxide, ethylene, and formate have already been synthesized electrochemically at partial current densities higher than 100 milliamps per centimeter square with Faraday efficiency higher than 60%. Among bioelectrochemical system, acetate is the state of the art, is over 6 times higher than the next closest species, and it can be made at almost 100% Faraday efficiency. For the indirect pathway, methanol and methane are really at the highest TRL in terms of technical barriers of formation, and they have very high achievable rates of formation. So this is a good graph which gives an overall summary of the current products and how far they are in the development value chain. And then in terms of overall timeline, this is a paper from Professor Ted Sargent from Toronto, which has a very simple title called What Should We Make with CO2 and How Can We Make It? They give a timeline over 70 years for different technologies. And if you look for first 5 and 10 years, this is electrocatalysis and photocatalysis are promised ones, followed by biohybrid, nanoporous confinement, using MOFs and geolites, chain insertion and molecular machines, for which a Nobel Prize was given a few years ago, are very long-term in the horizon. So in terms of, if I conclude all these technologies and their comparison, I see that thermochemical and bioelectrochemical offer the most feasible near-term opportunity for CCU, but they have also challenges like lower conversion efficiency in terms of thermochemical and limited product distribution for biochemical. Only C1 to C3 are the main products that are made. Whereas the direct electrochemical pathway indeed show a long-term promise and can theoretically overcome these limitations, but have technical barriers for near-term adoption. In terms of product with highest ease of formation, carbon monoxide and methanol are based on TRL and conversion matrices are the nearest entry points. And in terms of conversion of electricity to chemical bond formation, it's CO and formic acid, which are the top-term targets based on SOT conditions. With this, I would like to thank all the funders who have sponsored our research. And these are all my colleagues from VITO who are actually involved in the Capture initiative and are handling different projects that we are busy with. Thank you.
Thank you very much, Deepak, for this great overview of different technologies. And so that brings us from basically talking technology all the way to now the other aspects than just the technology. We're going to look more at the framework around political, economical feasibility of CCU. And so it's really a pleasure to invite our second speaker after the break now. That is Philippe de Smedt. And Philippe is manager of lower olefins and aromatics at CEFIC. Now, CEFIC is the European Chemical Industry Council. And so from this position, he has a very good view on what is going on with the ETS schedule, where it is going, and also how complex it is for different companies to work together, which fits very well within our industrial symbiosis approach. Lastly, I also want to mention that Philippe is a guest professor at our Laboratory for Chemical Technology here in Ghent. So with that, it's my pleasure to pass the floor to Philippe, and I'm looking forward to your presentation. Thank you.
Thank you, Korneel. When I was contacted, I was asked to talk about symbiosis. I didn't really know what to say about that, but what I will do is to try to give you and place the CCU in an economic context. What are the, let's say, the playing field when you want to do a CCU project? What is it that you, in what markets are you arriving? So basically, I will take a number of topics and we'll dwell on them and give you some elements that play a role in this CCU. So first, I will give my overview of what CCU is. Then I will tell you a little bit about. We've heard about the methanol project, and I will tell you a little bit about the vision of the International Energy Agency on methanol. I will tell you about hydrogen strategy of the EU Commission, and then how does it link to the emission trading system. So Deepak gave you a very nice overview of CCU, everything that is possible. I just want to give you a context. When I think of CCU, I mean CO2 in itself is not a sufficient molecule to make interesting products. I need also hydrogen. So for me, CCU would be combining CO2 and hydrogen. I'm not saying this is exhaustive, but essentially the level playing field you get into is if you have hydrogen that you need, you could also use that hydrogen directly as an energy carrier. So when you do a CCU project, compare it to the direct use of hydrogen. Hydrogen can also be used to make ammonia. Ammonia has only today is used as a fertilizer, but these people that are producing ammonia are making a case to make that as an energy carrier. So that doesn't involve CO2, but it's a field that you know that ammonia are also positioning themselves as energy carrier. Now going to the CCU itself, basically I can either make methanol from this, and then I can use the methanol as an energy carrier. So I'm competing with hydrogen and ammonia, but, and these are let's say commercially available. You could use the methanol to make olefins, you can make aromatics, you can make other chemicals, and obviously you don't need to go in the CCU via the methanol route. You could go directly to make other chemicals like we heard from Deepak. But then the most important other one is that you can again use either via the methanol, via the methane. You can make, or directly Fischer-Tropsch, make synthetic fuels. And there we have a fourth one that can be used as an energy carrier. So that's maybe as a reflection. Now, methanol, we've heard, is the big project of Ghent. So I'd like to discuss with you what the International Energy Agency thinks about methanol and what their vision is on that. This is a report everyone can download for free. If you go on the IEA website, you have to register. With this, they sell their reports, but this one is for free. So the report is called Future of Petrochemicals. It dates back to, I think, 2018. And basically, it's saying the future of petrochemicals, what they do is, what does it mean for in greenhouse gas emissions? And these are reports written for, I would say, people in the administration, competent authorities, helping him to decide how can we as a country realize a path towards lower greenhouse gas emissions. So they've studied in detail the petrochemicals. Petrochemicals has 7 main building blocks, and I've listed them: ammonia, ethylene, propylene, benzene, toluene, xylenes, and methanol. I see there is a small mistake. The xylenes should be listed in the blue box with ethylene, propylene, benzene, toluene. We call them high-value chemicals. So you will see in the next slides that sometimes they look at 3 products: ammonia, HVC, and methanol. These primary chemicals basically account for 2/3 of the total energy consumption of the chemical industry. And these 7 blocks can all be made from fossil feedstock, which could be coal, oil, gas. They can be made from biomass. They can be made from waste such as biogas, plastics. And with the exception of ammonia, which doesn't need CO2, you can all make them from CO2 and hydrogen. Maybe one thing, so indeed it's the building block of the chemical industry. So if you have these components, you can make everything basically in chemicals. Now, what is the methanol market? Today it's estimated to be about 100 million tons per year. It is used mostly today as an intermediate to make other chemicals. 40% is used to make formaldehyde, and then from formaldehyde goes into plastics, plywood, planes, explosive, textiles. But you can also use it in antifreeze, you can use it in solvents, you can use it as fuel in vehicles when you transform it to MTBE, or some countries allow methanol to be in gasoline. And then these are running processes. You can use it to make olefins, MTO process, and an MTP, methanol to propylene. The other is methanol to olefins. These plants are running in China, and it's known technology. But what the future is they see this as a sort of energy carrier. So to make either synthetic fuels or direct use, or just a storage, a way of storing energy of the hydrogen. That is, hydrogen has a low energy density. If you transform it to methanol, you can have a much higher energy density. So this is basically one graph which shows, okay, methanol, you can make it from coal, you can make it from oil, you can make it from natural gas, bioenergy, and you can do via electrolysis, which means you do the hydrogen via electrolysis and you combine that with CO2. And what you see is basically how much feedstock do you require to make this methanol from the various, and you see you need quite a lot of feedstock when you go via the electrolysis, also high water consumption. Now, the IEA study is quite interesting. They look at 2 scenarios. It's a sort of reference scenario and a clean tech scenario. You may think that the future is what Europe thinks, which means 0 carbon emissions by 2050. This is a worldwide study, and maybe you could think less ambitious, but they try to sort of by putting scenarios that are nonetheless quite ambitious to reduce 25% CO2 reduction in the petrochemical industry. That doesn't mean that it's 25% overall, because they also do studies on refining and big world models of all industry. So this fits in a scenario that has a much higher CO2 reduction, and it fits, I think, in the 2 degrees scenario. But what it shows that this already requires a lot of adaptations if you go to the clean technology scenario. And what I'd like to show you is, first you will see that there is a big growth of the methanol market. And to show that, look at the bottom graph that shows methanol growing from 100 million ton to about 180 million ton in 2050. And then you also see that today a lot of that methanol is produced from coal, giving huge emissions, and mostly in China. And you see that coal will be phased out in this scenario. But what you see is the yellow one, it's the electrolysis, and you see that due to the way their models are built, we see the CCU to make methanol in Europe, and you see that we're anyhow a very small player in methanol, but nowhere else. You don't see any yellow anywhere else. So that's what you need to keep in mind. You will be producing methanol from CCU, and no one else will be doing it. In this clean technology, you see the 2 scenarios, the reference and the clean. And when you compare them, you see the emissions of CO2 in the clean. There is a big part, that's the reduction. You see that there is a big part where you see that it goes into storage. And that's the main difference between clean and the reference technology scenario. And you don't see a very big growth in utilization. Again, a bit of reflection that Europe seems to be the only one going that way. So it's much easier to store it than to utilize this. And hopefully, maybe in 5 years from now, IEA will publish a different study. And I've seen that there has been a discussion. IEA counts the formation of urea. So you basically, the CO2 you generate in ammonia production, you combine it with ammonia to make urea, and then you put it on the ground and it comes free again. They count that as CCU, and that's increasing a little bit. And they also assume that a lot of CCS will be used in the methanol process. Now, let me come to hydrogen. That's maybe good news for you. I invite you all to consult the paper of the Commission. I've given you the reference. It was published in July 2020. What Europe wants to do on hydrogen, which you will need. So Europe has the intention to install 1 million ton of renewable energy hydrogen by 2024 and 10 million ton by 2030. And that would be produced in 2 zones, one being East Europe and the other being, let's say, Spain, Italy, where there's a lot of sun. So they assume that there will be 2 regions where each of these regions will at least have 40 gigawatts of electrolysis units. The main production today of hydrogen is via steam reforming. In Europe, it's only via gas, not coal. The emissions, if you do that via gas, is about 10 tons of CO2 for every ton of hydrogen produced. Now, the current renewable hydrogen production, that means via electrolysis, is very small. Europe estimates it to be less than 3 or 4% of hydrogen production. We have at CEFIC have been trying to understand what the hydrogen market is. And today it's doing all the work. The on-purpose produced hydrogen in Europe is estimated to be anywhere between 5 and 6.5 million tons per year. And that is because I don't have all the data. I don't know how much is used in the steel. But what I do know is that in addition to the 5 and the 6.5, there is at least 2.8 million tons of hydrogen that is produced as a byproduct from other processes. And that will not go away because I want to shift from, let's say, this fossil-based hydrogen, the 5 to 6.5 million tons, to renewable, because that hydrogen, I don't make it on purpose. I want to make something else, and I get that for basically for in addition to it. Which means that knowing that today you only are consuming 5 to 6.5 million tons of hydrogen that is produced on purpose, and you want in 2030 to have 10 million tons, you need a significant increase in outlets. So that's a big opportunity maybe for CCU. And then finally, I want to tell you a little bit about ETS. So ETS, if you look at European greenhouse gas emissions, you will see that this thing comes from the Association of the Automobile Manufacturers. That's why they highlighted the transport sector. But you see the energy sector is responsible for 1/4 of the emissions, industry 1/5. You see that transport is very important, it's about 22%. You have the split between road, aviation, water navigation, railways. This gives you some idea. And what has Europe managed to do? Basically, this is the track record of Europe, and I think we can be proud of that. Look at first the gray curve, which shows how much the gross domestic product of Europe has grown. And over a period, we may not be anywhere near Chinese figures, but between 1990 and about 2018-17, our gross domestic product in real and inflation-corrected figures has increased by 60% from 100 to 160. But we've been able to do that with about the same energy consumption. That's the yellow one, and the blue one, we have been able to reduce our emissions by more than 22%. But you all know that there is this Green Deal, so Europe is stepping up, and I want to highlight in this one maybe the ones where we feel as CEFIC very much that we can contribute. One is the transition to a circular economy, then there is the one on zero pollution, on clean air, clean water, and then there is this big ambition to be climate neutral by 2050. What is this Green Deal? You should think of a framework where any legislation that will be issued by Europe will be judged against. I put something in yellow. I think that everyone has understood that if you want to do this kind of thing, we need clean, reliable, affordable energy. I think I've seen in the discussion, the chat, many people saying yes, but you all assume that's renewable energy. The reality today is different. So this is something that we as a chemical industry cannot do, but this will be the responsibility of the electricity companies to make sure they have sufficient amount of renewable energy. So what is one of the tools that has helped Europe to achieve that 22% reduction? It's emission trading system. It's a system that applies to all energy intensive industries and electricity producers and covers roughly 50% of all greenhouse gas emissions of Europe. If you're in the system, basically there's a market of CO2 allowances, and basically you have to always give back the same amount of these allowances as you've actually emitted. And you have to buy them at a cost that has been varying between something between €5 per ton and €30 per ton. But Europe is, they realize that we're playing in a worldwide field where not everyone is having a CO2 cost. So the ETS allows that basically some allowances are given for free to the industry, but that's basically only a small amount. It amounts to the performance of the top 10 performers. That was a benchmark, and that's what everyone gets. It's the European Commission that actually determines how many of these allowances are put on the market, and that they decide which ones are given for free and all the rest are auctioned. So basically this system is an incentive for all actors to reduce their emissions. We think it will at least exist until 2030, but what after 2030? And the real question here is how to create a level playing field. How do you make sure that the product made in EU with a high ETS cost, how can it compete with a product that has been made somewhere else with high CO2 emissions that were never paid for in those countries? Because they don't have a carbon price. So Europe is looking at alternative systems beyond 2030. The Commission view, basically they want to regulate the price. They see we give less and less allowances, so the industry have to adapt, and by giving less and less, price will go up. And unfortunately now I come to the bad news for CCU. The accounting of these ETS CO2 emissions is covered in a regulation called MRR. The MRR accepts that if you put it permanently in the ground, then you can basically assume it's not being emitted, so you don't have to pay for it. But if you really want to boost the CCU, any CO2 utilized in CCU, you would also not like to be accounted for as emitted. Yeah? So if I'm emitting CO2 and I would have to pay €50 for every ton emitted, and if I can avoid that by giving my CO2 to someone else that uses CCU, maybe that person is willing to, I'm willing to give €40 to that person because it will be still a net saving of €10 just to give it to someone else. So the one doing CCU would actually have a negative price for paying for CO2. However, today, the two main applications for CO2 are urea and melamine. They're not recognized. They can't be touched. You basically, whether you put it in urea, which we can understand because it's released as soon as it is on the ground, but melamine, it is incorporated for maybe 50 years before it's ever released. The actor that is producing that CO2 has to assume it's emitted. And we have proposed a CEFIC changes to that MRR for the new ETS period. We have said it should be taken into account that if you make CCU and you valorize it, then it should not be seen as emitted. And we have done quite proposals, but as you see, what we think is that the Commission is not taking it, and they will still consider CO2 not to be accounted for in CCU, so assumed to be emitted. So don't expect that you will get money for taking the CO2. That's what I wanted to say.
Thank you very much, Philippe. That was a great presentation. A lot of information. I'll have to look through it again and really think about it. What I learned from it as well is that we do need to work strongly on the ETS to be able to include more possibilities, not just for CCU, but for also other sectors. That brings me to the final part, the linchpin a little bit of our afternoon. We're moving into politics. And so to move towards policy, it's a pleasure to introduce Tomas Wyns. Tomas is a senior researcher at the Institute for European Studies at the VUB, the Free University of Brussels, who actually signed their agreement to enter in capture just in the past week. And so Tomas is over there working on European and international climate policy. And for example, he recently published an article or a report on the options to decarbonize energy-intensive industries in Europe and how we're going to finance these. So that comes very well aligned with what Philippe was presenting. So I'm looking forward to your talk, Tomas. It's a pleasure to hand over.
Well, thank you, Korneel. It's a pleasure to speak today. Also, congratulations to all the other speakers. I found the presentations today extremely interesting, and I have the advantage to be, I think, one of the last speakers, so I don't have to repeat other messages that have come before. I'm just going to see. Indeed, as you mentioned, with the VUB IES, we have published a few publications now on the transition of energy-intensive industries, both from the perspective of what are the technological options, what are the barriers, the opportunities, and what is the necessary policy, industrial policy to enable this transition. So I'm going to talk a little bit about the role of CCUS as part of the industrial transition, with a focus on what I call smart carbon management and the potential of carbon capture and utilization in the special location we take up in Flanders, the Netherlands, a part of Germany, north of France. The challenges and opportunities for industrial deployment, and then what would be the enabling policies and strategies to bring this transition about. So CCU, CCS, we see this as only a part, but an important part of the transition of industrial processes. There are other ways. I think in some cases you really want to prefer direct electrification of heat. At low temperature, this is definitely possible. At higher temperature, this is quite a challenge. But from an overall primary energy perspective, this seems to be highly interesting. Biomass as a substitute for certain materials or as feedstock is also interesting, but comes with a conditionality, of course, that it must be available, must be sustainable. And then indeed hydrogen, both as a feedstock and let's say steel, for instance, and as a heat source for high temperature heat could be interesting. And then you have the CCU and CCS options we have discussed before already. So these value chains, yeah, they've been mentioned before, and we can go via different routes to polymers, other high value chemicals. There is an energy link. There even might be a link with food production, with proteins. But in practice, roughly speaking, what do we need for an industrial large-scale transition with CCUS? And of course, you need capture installations, either point sources and maybe later direct air capture. This will be significantly large and quite a few of these installations. If needed, purification and liquefaction and pipelines for transport. We will need, and we've seen it before, as CCU, CO2 and hydrogen are these twins that often go together. So we'll need a lot of hydrogen. And of course, in that sense, hydrogen will need to be CO2 free, so likely electricity-based hydrogen. So we will need sufficient, adequate, cost-effective electricity. And of course, we will need new process plants, whether it's methanol to olefins, methanol to aromatics, or any other type of large process plants, a really large scale for CO2, to, for instance, the HVCs, which Philip mentioned. So what are possible business models? And it's a non-exhaustive list, but what can we do? We can produce our hydrogen ourselves, and of course use the domestic CO2 from point sources. That is an option. Of course, if you would think economically, maybe it's possible to import H2 or derivative of that very cheaply and use domestic CO2 to build up new products. Or we can do it the other way around and we say H2 hydrogen is so cheap in Chile or North Africa, so we will just export our domestic CO2, we will liquefy it, put it on a ship and import the CCU products that are derivative of that, or combinations of the above. But this is the area we should start thinking about. If we want to tackle climate change as a global problem, we will need to find solutions at a large scale, which means there will have to be global markets for both the feedstock, the inputs, and the intermediate and final products. And then a point, and that's not been touched upon that much today, and it is also one of the reasons I like the Capture project so much, is that we need to look at carbon in a holistic way. And it's been mentioned before, I think by Mark, carbon is an essential part of many critical materials, plastic, wood, paper, steel, and so on. The main issue we have with carbon at the moment is the release in a highly oxidated form, CO2, to the atmosphere and the accumulation in the atmosphere. So we will need to look more at the overall carbon efficiency in materials over their life cycle. And here, carbon efficiency you can consider as what is the loss of carbon in the form of CO2 to the atmosphere. So the materials as such are major stocks of carbon. So it's not only the carbon monoxide or carbon dioxide we can use, we will have to use these materials, and in particular the plastics, which contain a lot of carbon. They're energetically, they're very interesting, and we use them, we burn plastics quite a bit if it's not thrown into the oceans, but there is a high potential there to optimize circular use of materials. I go from plastics back to monomers and then back to polymers. So CCU should be considered as part of a circular value chain that seeks to maximize the carbon efficiency in materials. And this implies, if we again think at a large scale, the redesign of important industrial value chains. And it also means, and Philip alluded to it before, that policy must go beyond just addressing point source CO2 emissions. And while there is an incredible amount of literature on different types of CCU and hydrogen production technologies, we see more and more emerging literature on the integration of these processes in existing or virtual chemical clusters. And here on the right, you see an example, a recent paper by Thunman et al. From Sweden that seeks to integrate the plastic recycling, carbon utilization, but also flows of biomass into what could be a future petrochemical cluster. And it is now is the time where we have only 30 years left to achieve climate neutrality, to really start thinking at this system level and also prepare the policy to enable this transition. And I don't think it's a coincidence that we're having this discussion here in Belgium, at the Ghent University, Flanders, Netherlands, the collaboration in North Sea ports. We are part of an industrial mega cluster with a high presence of petrochemicals, ammonia, steel production still, and that is then part of a bigger cluster that includes parts of Germany, North Rhine-Westphalia. So if we talk about industrial transition, it will not be these small plants that will have to transition to climate neutrality. It will be these integrated clusters, and the word symbiosis has been mentioned before. We see the nice project in Ghent, Terneuzen, that focuses indeed on linking these different activities together, increasing carbon and materials efficiency there. It's no coincidence that this is starting to happen here. And from the literature we've seen, it will also be the only way to achieve climate neutrality in industry, certainly if you are working, starting from a brownfield existing infrastructure and production sites. And of course, talking about infrastructure, how do industries transition? And what comes first is a chicken and egg discussion. Do you start first investing in new process installations, including CCU, or do you wait for the infrastructure, build the infrastructure first, and then wait on the process installations? From, let's say, historical development in industrial clusters, it's clear that if you build the infrastructure, the investments most likely under certain conditions will follow. It's the same as with cycling. If you build a cycling infrastructure, the cyclist will follow. We see, of course, a lot of interesting projects, work in progress. The Portal CCS project, Antwerp at Sea, CCS carbon capture project, the work going on methanol, also part of the Small Delta Resources platform. Green Octopus linking offshore wind with carbon capture and utilization and hydrogen and so on. Again, zooming in on the region we were talking about, the largest integrated hydrogen network is again Netherlands, Flanders, part of northern France. The links to the North Sea are going to be essential for carbon capture and storage, which will also have to be part of the solution. Also, what we saw from the IEA study before. So again, this will be a big challenge. We will need CO2 infrastructure, hydrogen infrastructure, and if we're going to produce the hydrogen ourselves, we're going to need quite a lot of infrastructure related to electricity. Other challenges, major challenges, capital expenditure, but also the technology value of that. And it's been mentioned before that we have a lot of great research going on, but mostly on smaller scale. It's already a challenge to scale up to TRL 3, 4, but then we enter this big value of data where you need tens to 100 billions of euros to scale up to demonstration. And that is something where European policy has become really aware that they need to step in, that the illusion that a carbon price on its own would drive the full innovation chain from the lowest TRL to deployment as is an illusion as such. And therefore there is this innovation fund, tens of billions of euros will be reserved for, if I'm correct, for the transition of industry together with other European funds, but with a focus on a demonstration first of a kind, but also partially operational expenditure support that we've seen before, that methanol, for instance, ethanol, it will have it extremely hard to compete with some of the high value chemicals, in particular ethylene, which is a market more or less oversupplied at the moment. So that will be a tough one. So you will need instruments to make sure that these new technologies can be demonstrated, but also that they have time to mature, to optimize, and hence lower their OPEX. Further OPEX, and again for CCU a simplification, CO2 plus hydrogen, and then the hydrogen itself will require a high amount of electricity. So the electricity price will, in most cases, not in all cases, basically be the make or break of CCU. And you can think about what would be the ideal price. We looked into this, and we just used a basic heuristic rule that if this is going to be one of the most electro-intensive processes around, in particular through the use of hydrogen, it will have to compete with prices that are allocated currently to highly electro-intensive processes such as primary aluminium. What's the power price you can accept as a primary aluminum producer to be competitive? And then we're entering really in the areas of kilowatt hour prices that are going to be well below 40, 30, 20 euros per megawatt hour to make these technologies competitive. But also the supply of electricity. work by ourselves, but also by Euroelectric estimates that if you want to achieve this industrial transition, and that's not only hydrogen for CCU, but also direct electrification, for instance, there could be up to a demand of 3,000 terawatt hours from industry alone in 2050. And 3,000 terawatt hours is the current economy-wide demand for electricity in the EU at the moment. Can we supply that? Well, how can we supply that in a green way and a cost-effective way? I'm showing here a presentation from Wind Europe with an estimate on the potential of offshore wind production capacity in northwestern Europe, and there is an estimate, and definitely with the offshore wind technology, floating technology becoming more and more available, of 6,000 terawatt hours economically per year in this area. So this is highly interesting. And why is this relevant? Because in the history of industrial revolutions, each industrial revolution has always been driven by an energy revolution. I think of coal driving the railroads, driving the steam engine, driving the steel production to make this all happen, or oil and the automotive, and later the whole plastics and chemicals industry, or the wide use of electricity that enabled the IT revolution and basically changed everything. So it is possible that we get this energy industrial symbiosis between, for instance, wind, but in the south of Europe it can be solar for sure, and industry, because we will see the development of value chains that produce steel, that produce plastic, that produce a lot of non-ferrous metals for these new energy production. And then that offshore energy production or other renewable energy production will of course drive the industrial processes. So it could be the sign of a new virtuous cycle that mimics other industrial revolutions we have seen in the past. So the policy framework, and we come to the core of it after this long introduction. Two elements, a strategic element and then some practical suggestions and considerations. If as a government you want to succeed in this industrial transition, and I repeat, it's a transition over 30 years. If you put it all together, it's the biggest industrial revolution since the Industrial Revolution over a time period which is almost half. It's going to be extreme. You need a strategy. You can't do this without a vision, medium-term, long-term vision. So you need a strategy on how to achieve this. Where are the priorities? Where are you going to put your money? What are the overall technology baskets that are seen to be relevant for the region or the economy as a whole? Secondly, the acknowledgement of smart carbon management. So really, or put it otherwise, circular economy must be the core of the climate transition. And we've looked at quite a few models and studies, and without high levels of circularity and material efficiency and reuse and so on, it is going to be almost impossible to cost effectively become climate neutral in 30 years. CCU will be a hydrogen dependent technology, so you can't do the transition, you can't do the CCU without a hydrogen strategy. And then again, the hydrogen deployment requires a strategy on electrification, both networks, grid reinforcement, but also the supply and the security of supply. We need a strategy on that too. And you need a strategy on the infrastructure for all the rest of the hydrogen, CO2 infrastructure, but also importantly links to the circular economy, the reverse logistics of making sure you create a reverse value chain of end-of-life materials, plastics, into your primary production of, for instance, chemicals again. And then policy initiatives to close off with. How can we make this more specific? It's always nice to have a strategy. There is this joke in Flanders, if you have a problem, you just make a task force and then the problem is solved. No, you need also additional stuff on top of that. So infrastructure, basically you need a 10-year development plan to make sure that the hydrogen, CO2, your power system is ready to integrate these CCU and other electricity-based technologies that likely will come online on a large scale in the 2030, 2040s. We'll also need a regulation and a governance system. Who owns the hydrogen network? Who runs it? Who is the regulator? And so on. Those are things that are not really at the table right now. We need to develop the reverse logistics, and that can be regulation for circular materials. Of course, you must be opportunistic, and now is the time to do this investment because the European Green Deal, new European projects, financing is available for these infrastructure, in particular if it's cross-border infrastructure. And we've seen the example of the Netherlands and Flanders before, instruments such as Connecting Europe Facility, industrial projects of common European interest, the EU recovery funds, the Next Generation EU. There is a lot of attention going into that. So as a policymaker, you should be aware of that and make sure that you use the opportunities that are given there to develop this. CapEx and OpEx support, we will need to finance these pilot and demo installations, for instance, via the EU ETS Innovation Fund, but also as a national or local authority, you will need to develop co-finance instruments, industrial investment banks, and so on. We'll need to look into operational expenditure support. There is an idea on using so-called contracts for difference, which has been used in the renewable energy business, where you don't give a pure subsidy for the production of low CO2 materials, but only the difference of price between, let's say, what is paid on average in the global market. It's not going to be very easy to implement this, but it's an idea that is going around quite wide, both in Brussels and outside of Brussels. Or the use of standards, that's basically saying X% of your materials will need to be coming from circular or CO2 utilization sources. Of course, brownfield conversion support, you will have to demolish or adjust existing infrastructure, existing plants to make sure they work in a low carbon manner. Regulatory elements, and it's been mentioned a few times before, we need to have good, transparent life cycle assessments and accounting for CCU. Well, how much of CO2 is now removed from the atmosphere? Can we think about, well, the removal is equal to the average lifetime of a CO2 molecule in the atmosphere, let's say 100 years. If you can ensure that the CO2 you utilize is gone away for, or is not being released in the smart carbon fashion for 100 years, you could get a full credit. But there are other ways to look at this, but it's quite urgent. If you want to develop policies that support such instruments, such technology as CCU, you need to also make sure that you can measure it in a consistent and adequate way. We need to set up these circular material value chains via standards, and standards is a very powerful instrument. In Europe, we're extremely good at setting standards basically on everything, and you can think of the carbon intensity of the material in a car, or the amount of circular material in packaging. These can be standards that can become binding, reinforced, can become stricter over time. And if we look at the history of industrial innovation, most radical innovation has been driven by the opportunity of a market. And through standards, you create a market. So you will create a market for technologies that might be too expensive to operate without these standards at the moment. And then, of course, Philip mentioned it before, consider allowing negative emissions in the ETS, for instance, via CCU technologies or CCS with bio-based inputs and so on. But you will need to have very strict, verifiable LCA rules in place to be able to do that. And then, of course, we've seen a lot of amazing technologies here today, and quite a few of them are coming from Horizon 2020, Horizon Europe, or the Catalysti moonshots, or other similar processes outside of Europe or Belgium. You need this mission-oriented R&D. You need to put out these challenges through the scientific community, innovation towards more cost-efficient hydrogen production. Of course, if we can shave 1-2% more of the efficiency there, this will will have a humongous impact on the overall industrial transition. Innovation towards, of course, cost-efficient CO2 capture technology, and we want to make sure that the CO2 we're going to capture, that doesn't cost that much, and also that it doesn't place too much a burden on the emitting side of the industry. And then we've seen a lot of things before, improve the CO2 conversion to materials via all kinds of different routes, and a lot of exciting things I've seen so far, including maybe even in the end CO2 to proteins, to animal feed, to meat replacement, and so on. And this is in a nutshell all I had to say. So in the summary, CCUS likely to become an important or even essential element in the industry materials transition. We'll need smart carbon management, and that is the link between CCU, circular materials, bio-based materials will be essential. We need long-term strategies, and we will need to enlist a combination of policies in areas of infrastructure, CapEx, OpEx, R&D to ensure a broad and timely transition towards 2050 climate neutrality. So thank you.
Thank you very much, Thomas, for the end of the last speaker to really bring this vision together. Again, a talk with so much density and information. So the whole session is going to be recorded, and so we'll find the best way to make this available. While I'm asking for our different speakers to also come online with their video so you can all see us, there's a very short poll that Elise wanted to organize, so I'll pass the floor on to her while our, it's already popping up, while our speakers are coming online. And I also have to tick very happy. You need your expectations. All right, don't push end poll, just leave it going while we're coming online. So while you're filling in that poll, I'll take the liberty of already starting. So we have on board, if I'm not mistaken, Mark, Saeys, we have Simon Corte, we have Deepak Pant, I see. I don't know if Wim Van der Stricht has reconnected for the session. Great, Wim, welcome. And then we have Philippe also sitting with us. You see the overall screening here. So I think we're complete. And let me start the debate. I'll try to keep it rather brief. With just a more general question, and I think I'll start with Thomas, our last speaker, to answer. So if you look at CCU, the typical criticisms are twofold, right? That you need a lot of renewable energy, but as we showed, there's going to be 6,000 terawatt available potentially. So can we say that for CCU, there is actually enough energy potential? We just need to make more electricity and just make more and more and more. You see recently the record price for photovoltaic in Portugal is 1.3 cents per kilowatt hour, including storage. So we just make more power. Is that a key solution, Thomas?
Definitely. So the one transition will drive the other, but of course we must also watch out that we're not seeing CCU as, let's say, a hammer and then fix all nails. So if we're going to massively make e-fuels with CCU, this might be counterproductive also from a CO2 perspective. So must be careful where we apply it. If we can store the CO2 in materials, that would be a prime goal for CCU.
So we're going to need something like a combination, of course, electrification of transport. And then you look at CCU and the economic case on the long run of making products relative to CCS, which in the end is a cost. So maybe Deepak or somebody else who feels answering is like, is there a future for CCS on the long run?
Yes, thanks, Korneel. Yes, I also discussed it with my colleagues who are more policy oriented, and especially Metin, who you know, who deals with these topics. And the point is the target now, in Flanders, we are talking within moonshot, let's say climate neutral industry by 2050, but the scenario analysis shows that it will be actually CO2 neutral in 2070. So this requires not only CCU, but also CO2 negative solutions, which is of course CCS. So CCU towards building materials so that you just capture it and store it for a long term, rather than the story of CO2 to fuel and back to CO2. Because this was also raised by a couple of participants that what if you convert something to fuel, you burn it immediately and it goes back to the atmosphere. So CCS will be a part of long-term solution as well.
So that kind of gives the feeling that, okay, we're going to need negative solutions. So in the long run, to capture also what was historically more emitted or is turning over. So is there a role in those stories for aspects such as direct air capture? Maybe Mark, you want to say something? I know you have some opinions on direct air capture. Is that going to play a role, you think?
So to me, CCS is a solution for the fossil fuel industry. As long as they keep producing fossil fuels, they need to do something with the carbon they take above ground. And so I would really say, as long as we use fossil resources, we need CCS. And hopefully that drives up the cost for those fossil resources enough to make CCU-based materials cost competitive, especially with rapidly decreasing cost of electricity. And direct air capture, well, again, it depends on the cost or value of that CO2. If we're willing to pay $200 per barrel of oil, then that $200 can easily cover the cost of direct air capture. So again, I would link the cost of air capture to the value of what we want to pay for fossil fuels. Mm-hmm. Maybe at $200 per barrel, a Tesla car becomes much more interesting to drive around with for most of us. But at this point, that economics isn't there yet.
I guess entropy is always an expensive one to fight.
Well, T delta S is delta H, so entropy is energy, right? In some sense. So as 1% of the solar energy is enough to cover our energy uses. So I'm not. Energy is available. It's just a way of converting it from photons that are gone in micro or nanoseconds to chemical building blocks that are here for 10, 20 years. It's a time scale issue more than.
So it seems to me also that a lot of that challenge is going to be put on industry. I mean, we're going to also rely on creating a drive. I mean, there's a policy framework, but at the end of the day, many companies will have to engage in CCU or CCS. And so I'm curious a bit to hear from Wim, what he thinks now from an industrial perspective. What are really going to be the game changers? What is companies really going to get across beyond just an ETS or a standard?
Well, thanks, Korneel. Maybe to first also comment on the CCS topic. We also see the need for CCS, specifically on the short term to meet our targets, and also because we have no solution yet to replace all the fossil sources that we use. You know, in the blast furnace, we have to use also coke next to the coal. And for that, there is no, let's say, economical large-scale solution yet. So we still think on the short term, we will certainly need CCS. But at the stage that we find a solution for that, technical solution for that, we don't really see a need for CCS. I think then we can go fully the CCS route and hydrogen route to become carbon neutral. What will be important, I think, to really make a breakthrough, I think you mentioned it, we need to have massive green electricity to become, let's say, cost competitive in our production. The green electricity has to be cheap, because otherwise we will not be able to compete. Even if we would be able to reach a level playing field in Europe with respect to the rest of the world. We will still have to be competing with the price of an oil barrel. And when that remains very low, then there will be no incentive, economic incentive, to go fully to the CCU route. So I think that will be the main game changer. So we need some incentives to increase the price, as also Mark was saying, to increase the price of the fossil sources, because otherwise it will not just...
That it comes back indeed to having renewable energy at a low cost.
Yeah.
That's why I mentioned this example of these now auctions that they have on solar energy. It's so spectacular that you see 1.3 cents sales price of electricity at a solar plant. We used to do a lot of process calculations taking into account why electricity is going to cost 10 cents per kilowatt hour, but the game changes if you can really structurally get it down with an order of magnitude at some point. And so it's really also hopeful that we see this evolution now coming. So,
maybe if I can add to that, sorry, we will not only need more electricity, but with the production of renewable electricity, the steel intensity of this electricity production will also increase. Because if you see how much steel you need for a wind turbine or a solar panel, it's a lot more compared to, let's say, a coal-fired plant or a nuclear plant. So this transition will also need a lot more steel.
So yeah, it sounds as if you see a good opportunity there too.
Indeed.
So that brings me to what I found a quite striking finding, and that I thought is this geopolitics. When Philip mentioned, well, you know, it's Europe that's really the one that focuses on CCU, and the rest seems to be marginal in terms of looking into this. Is it some kind of supply that Europe wants to be more independent on its chemical provision and therefore has interest on CCU, or what do you think is the reason?
I don't know, but let me try to answer a different way. I think I support the statement that CCS will be a solution on the short run, that we would absolutely need to meet this 2 degrees or even 1.5 degree Paris agreement. Because it's a technology that is relatively, I would say, ready to apply. But it's only a cost. It doesn't add something. Of course, it's much better if you can actually use this molecule to make something good. And so the real challenge is first to make these processes competitive. And for the moment, we see that they have a penalty. The projects also against students, we've looked into projects and we couldn't make one that made economical sense at the current CO2 prices, electricity prices. So, but that might change if people start to take into account the cost of CO2 worldwide and start to. So I think also Europe has this vision of circularity, and CCU is a perfect way to keep your carbon into the material chain and not let it flow out. So I think it's an opportunity for Europe, and the real challenge is how can we give the air such that these processes can grow and that they are ready by the time the economic conditions are such that the current fossil production, that is with current fossil prices that are very cheap, especially due to COVID, but that's maybe transient, it is very difficult to compete with these processes. Yes. Answering on the capture in the air, I think one of the economic logic is the bigger you build the plant, the cheaper your production costs come. If you do, let's say, the classical methanol, if you would, like Arcelor, have the biggest CO2 emission in Belgium, it's very concentrated at one place. So you can get at one location a lot of CO2. If you have to, and then you can build a very big plant making something else, which will bring down the production cost. If you capture it from the air, you get a very distributed system. You build small plants, or you build a very big logistic system transporting all that CO2 to a central location.
Yeah.
And that is very similar to the biomass case, where the whole discussion is, can we concentrate biomass at decentralized locations so that it becomes easier to transport and then transport to one big plant that makes something.
Transport is always an interesting one. I agree with that. I mean, you see this evolution towards decentralization of electricity production relative to the centralized production. But that model, like for photovoltaics and rooftops, doesn't work for everything. Like water is another sector where transport is very challenging. If you have to put a tank of 10 cubic meter of water on a boat to supply drinking water, it is nothing but it weighs 10 tons, and you're shipping around 10 tons of just water. So important in this drive, I guess maybe in Europe, is also to see the good examples, and this is where I move towards Simon, where you see now in our harbor and other areas around us, you see these stilanols coming up, you see the North CCU methanol, and North CCU Hub and North Sea methanol projects coming up. They have the feeling that now that we're working on these projects, like are other companies from, let's say, our harbor or around starting to turn and look at these living labs that are starting to emerge? Is that a very important catalyst? Do you see that interest growing because you're doing it?
Yes, I really think so. So I think it's a matter of creating the good environment, the good atmosphere, and then having the right local incentives, let's say. I think it's also a matter of de-risking. You should have to de-risk the industry, and the de-risking process depends very much on where you are in the value chain. If you are operating a methanol plant, you want someone to purchase your methanol, and not that he's buying grey methanol at some point and comes to you when you're economically more interesting. If you're operating an electrolyzer plant, you want secure access to renewable energy. So I think it's a matter of supply and demand, which depends very much on where you are in the value chain, making it a rather complex story. And that's where the role can be for policy and for incentives. I also want to stress that it's, in my opinion, there has been too much focus on presenting one approach or one technology versus the other. If you see what we're doing in the harbor of Ghent, we have this very nice roadmap, and in the end, by 2040, we might end up with a potential saving of 1 or maybe 2 million tons of CO2 per year out of 22. This means that there will be a lot of other technologies, approaches, innovations needed in order to do that. Also, first place, reduction of the emissions.
Yeah, I really agree with you on that point, how it is an and story, not an or. And there are so many cases where indeed people are comparing technologies to say this is the best. There is no best technology. There is a right technology, indeed, the right process for the right place. And I think that positivism is also necessary to really also look in a positive way at the different technologies and the alternatives, and not try to identify the most promising, but just identify all those that make sense at whatever scale they would fit. So to end, it's 5 p.m., so we need to close off very soon, but I want to end up a bit on a more holistic level with our last speaker, because we've been really focusing today for a large part on technicalities, on the industry, how the network is together. But at the end of the day, things are only going to happen when society wants it. And I'd like to have your opinion, like what arguments are now really going to be the drivers for the general public, for society, to want what we have been discussing this afternoon? I'm sorry if I'm putting you in front of an impossible question, but I'm very curious to hear your opinion.
Maybe I might give you a controversial answer. Maybe Well, I have these earphones in it. They're designed by a big American company. I don't notice I have them in. So maybe, as a metaphor, society wouldn't care that much. As long as the service, the product they care about, the quality of life remains good, society won't care that much. And I might even make a stronger point. If we start making plastics or steel with CCU, CCS, all these basic materials, the final consumer might not even notice it that much in the price. And that's maybe a bit of homework for everybody. You can calculate it yourself. If polyethylene becomes 100% more expensive because we will use CCU or something else, what will be the price increase of a Coke bottle? It will be barely noticeable. If steel becomes 200 euros per ton more expensive, what will be the price increase of a car? 15,000 euro car, you barely will notice. It's crucial for the producers, but final consumer, society as a whole, might see in the future, if we put the right policies and measures in place, products that satisfy their general needs, that might be circular, and they might have to recycle their bottles and so a bit on, but in general might not see that much of a difference. As today, we don't really care where stuff comes from. Maybe that is not going to change. Right. I'm sorry for the depressing answer, but
it is a bit. I mean, I find it very interesting. It's a very controversial answer you're giving us, because what you're saying is sustainability is all about price elasticity, correct?
Not really, to the contrary. I think that it plays a role.
How much are you willing to pay before you change your behavior?
No, because even if we put a carbon price of 200 euros per ton in place, the price of some of the final products would barely change. And that is why I'm more of an advocate for standards, that the standard will be your product must be made clean, must be made with X% circular materials, because the final consumer won't really see the difference. But for the producers that produce it in a clean way, they have this margin they need to capture, and they can only do that if there's a market to capture that margin. So I'm actually going a bit against the elasticity as a single tool.
I actually find a more positive story then than to say it's as brutal as just price elasticity. So with that, we've slightly went over time, for which I apologize, because I believe it was a very exciting afternoon. I thought it was very interesting to see all these different aspects. So I want to thank you all very much. First, to all the listeners to join us this afternoon, to listen in, to ask many questions, which we'll try to answer later on. And of course, most importantly, I'd like to thank the very eloquent and interesting speakers we had this afternoon. So to thank them, we're going to give them something special, which you can see here, which is a very popular gin. And it adds a little bit to, well, one of my popular gins. It adds to sustainability because this is a gin that is fully distilled with solar energy, with a solar boiler. So it's like Mark says, let's keep the photons longer on Earth. What better way of keeping it on Earth than in solar distilled gin? So the speakers that were not here today from a distance, you will receive this via mail or in person when we meet again. I want to again thank you all, and with this I'm very happy to close down this afternoon session and announce that it's Friday evening. It's drinks o'clock, right?